Everything we do with projectile motion has to be solved x and y separately. Even our kinematics equations take on new subscripts to solve x and y separately. Okay? So we've got to start thinking about those as individual parts of a problem. Okay? We've got to think about horizontal motion and vertical motion as individuals because they don't account for each other. They don't make any difference for each other throughout the motion. Okay, so we're going to start talking about projectiles today, which means they have both horizontal and vertical motions. Okay, so projectiles is any object that moves through the air in 2 dimensions. So it's moving in both the x direction and the y direction. Okay, so these are things that are actually moving through the air. These aren't flat coordinate plane type problems. These are things moving through the air, flying through the air. Most of the time it's something thrown or kicked or dropped or rolling or something like that that we'll look at projectiles. Okay, so 2 dimensions. Throwing a ball, long jump, kicking a football, all examples of projectile motion. Okay, anything that goes up, reaches its peak height, and comes back down while traveling a horizontal distance. Okay, so those are all some examples there. When we look at projectiles, we don't care about the motion of the kick or of the throw or of that. We don't care about any of that. We care about the object once it's released, once it's in the air by itself and it's moving freely through the air. That's what we care about. We don't care about the speed at which the person's foot was moving. Okay, we care about the speed of the object once it becomes a free falling object. Okay? So we're only looking at motion after it's been projected and is moving freely through the air. Okay, it's flying through the air. That's all we care about. So if something is moving freely throughout the air, what do we know about free falling objects and their acceleration? What do we know about the acceleration of a free falling object? Negative 9.8. The acceleration, the vertical acceleration of an object is negative 9.8 meters per second. It has to be made clear that that's its vertical acceleration. Okay, and it's acceleration due to gravity. How do we abbreviate negative 9.8 in our equations? What variable is that? G or A. Yeah, whichever way you want to think about it. G or A. Okay, little g. Right, so that acceleration is our vertical acceleration. Always, always, always going to be our vertical acceleration. Okay. Galileo was the first one to accurately describe projectile motion. He was the first one to tell us that horizontal and vertical components behave separately from each other. One does not depend on the other. Okay, so how fast an object is traveling horizontally has no effect on its gravitational acceleration. Okay, or its acceleration due to gravity. Okay. So when we're talking about projectiles, we have a few different convenience things that we can always assume. Okay, so we say for convenience, we assume that air resistance is negligible or negligent or however you want to say that. Okay, we're going to ignore air resistance. Okay, we assume that our motion always begins at time equals 0. Okay, we've made that assumption before, but we're just kind of reiterating that our time is always initially 0. So that means technically our delta t, or the t that we plug into our equation, is how much time it takes for the whole process. We're always going to assume that our motion begins at the origin, which means x equals 0, or x sub o equals 0, and y sub o equals 0. I didn't put those subscripts in, but that means our initial x and our initial y should equal 0. So if it makes you feel more comfortable to have the little subscript 0 in there so you know we're talking about initial, you might want to go ahead and do that. Okay. The reason that works is because we get to pick our origin. We get to pick where the motion begins, right? We get to pick where the origin is. So we're always going to pick the beginning of the motion. Okay, which means that our origin would be 0. Once the ball leaves the table, it starts to experience gravity. Okay, yes, it's experiencing gravity while it's on the table, but when we're talking about its free fall, it's going to start experiencing a downward acceleration. Okay. since it doesn't start experiencing that acceleration until it leaves the table, we've got to understand that as something is rolling here, and as it leaves the edge of the table, it has no vertical velocity to begin with. Okay, it starts with a 0 vertical velocity. Because at this point, right now, it's only moving horizontally. It's moving just off the table, and it's not moving vertically yet. Okay? So our v sub y0 would start at 0. Okay, our initial vertical velocity would start at 0. And this is for rolling objects, rolling projectiles. Okay? As time goes on, it will gradually increase. So your final velocity would have a larger number. But it would increase because of our acceleration due to gravity. Okay? And I'm not sure if your book calls this a sub y or if it calls it g, but it's still negative 9.8. Okay? Our acceleration in the y direction, that's all that's saying there. You could label that g if you want. That's up to you. Okay? But it's still going to be negative 9.8 meters per second. You don't have to write these equations down. I'm going to give them to you in just a second. Okay, but we're going to use our kinematics equations and we're going to adapt them a little bit for projectiles because some things we can assume, some things we don't. Okay, so just remember that for rolling projectiles, things that roll off a ledge, off an edge, they start with initial horizontal velocity only. Okay, because it's not moving up and down yet. We're going to look at those equations in a second. All right, the horizontal components. For all projectiles, this is important, there's no horizontal acceleration. Okay? You don't have any horizontal acceleration in projectiles. Things don't speed up and slow down on their own as they're moving horizontally. Okay? They speed up and slow down vertically as they reach their peak height and begin to fall again. But as they move horizontally, they do not speed up or slow down. So you never have a horizontal acceleration in projectile problems. Okay, never, ever, ever. Okay, a sub x is always 0. Since our acceleration is 0, that means our initial horizontal velocity and our final horizontal velocity would remain constant. So those would be equal to each other. Okay, that means v sub xo, or v sub ox, however you want to label it, would equal v sub x. Right? Initial horizontal velocity would equal final horizontal velocity. That's because there's no acceleration in the horizontal direction. Things don't magically get faster and slower horizontally by themselves. Okay? Or a ball that's dropped at the same height, which would hit the ground first? One that's dropped, raise your hand if you think the one that's dropped. If you think the projectile, raise your hand. If you think same time, raise your hand. If you don't have any idea, raise your hand. An object projected horizontally will reach the ground the same time as a dropped object. Exactly the same time. You want to know why? Horizontal and vertical components are separate. As long as they're dropped, as long as they are released from the same height, vertically they travel the exact same speed. Okay? Horizontally, one will travel a farther distance. They're not going to land in the same spot, but they're going to hit the ground at the same time. Okay? That's because horizontal and vertical components are separate. Okay? They're dropped from the same height. They have to be the same size. Okay? They have to be things that look similar, but they have to be separate components. Okay? So vertically and horizontally, they don't match, okay? Galileo said that, and here's a time-by-time frame of this exact demonstration, okay? So the yellow one is projected. It's traveling both horizontally and vertically. The pink is just straight dropped, and voila, they hit the ground at the same time, okay? That's because vertical and horizontal components are separate. They have the same vertical components. They're dropped from the same height. They're both experiencing acceleration due to gravity. They both started with an initial vertical velocity of 0. Okay, remember, because projectile things that roll or things that fall off the ledge, things like that, have an initial vertical velocity of 0. Now, if I throw the ball to the ground and I drop the ball, which one would hit first? The throw, right? Because I would be having an initial vertical velocity on that object, and it would be going faster to begin with, which means it's increasing at its velocity with gravity as well. Okay? Make sense so far? All right. So what I want you to do is look on page 60 in your textbook, And table 3-1 is going to give you your regular kinematics equations that we already know. Okay? But table 3-2 gives those abbreviated equations to use specifically for projectile problems. So you need to have these equations in your notes and on your equation sheet if you would like that. Okay? So you need to label these as projectiles. Label them X. Here's my equations for horizontal. Here's my equations for vertical projectiles. Remember, because they are totally separate. So you should have some projectile equations, you should have X, and you should have Y equations. Okay? All right, so when we start solving projectile problems, just like any other problem, please make sure that you read the entire thing. Don't assume you know what it's going to ask for. Okay, read that entire problem. When we're looking at projectiles, it's really important for you to include the origin. Okay, draw the diagram, include where your origin is by using those crosshairs so that we can see where the origin is. Your XY coordinate system, you make sure you always choose up as the positive direction, to the right as the positive direction, things like that. Okay. We look at X and Y motion separately, make our list of our variables. If you think that you can get through these problems without listing your variables and knowing what you have and knowing what you don't have, you're probably wrong. Okay, you could prove me wrong, but I would feel more comfortable if you would just do it. Okay, just list your variables, get used to doing that. It will make your life easier, I promise. Okay, I promise. All right, so make sure that you know what variables you have. It's going to make picking your equation a lot simpler. Okay? As you're making your list, you can think about some of those assumptions we talked about. Okay, we can always assume that initial positions are both 0, which means x sub o equals 0 and y sub o equals 0. We know that our velocity in the horizontal direction, or v sub x, never changes, okay, because we have no horizontal acceleration. So we know v sub x equals v sub x o. Our initial horizontal velocity equals our final horizontal velocity. Remember, at the highest point of any trajectory or any projectile, when something reaches its peak height, what would its vertical velocity be? 0. When something reaches its peak height. So let's talk about this. Here's my projectile. It starts out at this angle. It's flying through the air. Okay, when it reaches its peak height, right here, is it moving vertically at all for that one little millisecond that it reaches its peak height? It's not going up or down, okay? So that means v sub yo at peak height, I'm sorry, not v sub yo, v sub y at peak height would equal 0, okay? What about horizontally? Is it still moving horizontally at that point? Yes, it's still moving horizontally at that point, okay? Because there's no acceleration in the x direction. It doesn't slow down or speed up at all through the process. So its speed horizontally is constant throughout its entire motion. Okay? Vertically, you have fluctuating velocities. Horizontally, you do not. Okay? Velocity before hitting the ground is generally not 0. When we're talking about projectiles that come up and go back down, we're not looking at when it crashes to the ground and stops. Okay, so if it asks how fast is an object going before it hits the ground or when it hits the ground, we're looking at the little millisecond instant before it hits the ground, not when it hits the ground and comes to a stop. Right? Does that make sense? We've talked about that a little bit before. All right, good. And think before choosing an equation. Make sure you're doing x and y separately. You're looking and you're labeling all of your variables correctly so that you can choose a correct equation. Okay. Speeds horizontally off a cliff that's 50 meters tall. How fast must the motorcycle leave the cliff if it's to land 90 meters from the base? 90 meters from the base. Okay, so I'll give you a couple of seconds to get this written down. I'm going to go ahead and draw our diagram here, what we think this looks like. Okay, so here's my little driver. My origin I always pick at the beginning of the motion, so I'm going to pick the top of the cliff to be my origin. Okay, which means y sub 0 would be 0, x sub 0 would be 0. Since those two are assumed, those aren't ones that you have to write down every single time. You can, but you don't have to. Okay. What do we know about y final? What do we know about our final vertical position? Negative 50, because we're landing 50 meters below where we started. And what about our final horizontal position? 90 meters. And is it positive or negative? It's positive, because we're landing to the right of where we started. Okay, very good. So what are we overall solving for here? What's our overall goal? Velocity in which direction? Horizontal. We're looking for horizontal velocity, okay? So we're going to solve first for time, and then we're going to be able to solve for horizontal velocity. So let me put my variables back up here. Okay. Let's take a look at the sets of equations that we have. If we want to solve for initial horizontal velocity, that's our overall goal. The only equation that we could use to solve for that would be v sub x equals v sub xo. And that doesn't do us any good because we don't have our final vertical velocity either. We could use our equation x equals v sub xo times t. And we have our x, which is 90. We don't have time, so we're going to have to solve for time. Okay? So that's another variable that we've got to bring into this equation. Okay? So now, since we know that time translates to both our vertical or our horizontal equations, let's take a look at our vertical equations and see which one we could use to solve for time. Okay? Do we have any of our... What do we know about our vertical velocities right here to begin the problem? Yeah. Good, very good. Initial vertical velocity, so v sub yo is 0. And the reason that is because he's leaving the cliff horizontally. So the second he is off the cliff, he's traveling only horizontal for that instant that the motion begins, before gravity really starts acting on him and he starts picking up speed. So do we understand why it's 0 there for v sub yo? Yeah, or kind of. Okay. Anytime we're rolling off a cliff, anytime we're doing something from a height and we're falling, we're going to have a v sub yo of 0 almost all the time. Okay? Unless we throw something in the air or things like that. Okay? So v sub yo is 0. Does that give us a little bit better clue for which equation we could use? Do we have one now that we could use? Okay, I think this y equals y sub o plus v sub yo t. 1/2. Right? Can we use this one? All right, good. So our y we know is negative 50. For these rolling projectiles, these two terms are almost exclusively 0. So we get to leave out two whole terms. 1/2 negative 9.8, and we have t squared. Okay. This accounts for the entire projectile. We're not dealing with peak height here, so that means we're not looking at half the motion. We're accounting for the entire motion. Okay, so we don't have to worry about multiplying the time by 2 or anything like that for this problem. Okay, so negative 50 equals negative 4.9 t squared. That means our t is equal to I got 3.2 seconds. All right. So we've got our time. Now we're going to be able to use our equation to solve for our horizontal velocity, which was our first overall goal. And we're going to use the equation x equals v sub xo times time. All right, so now we know that 90 meters is equal to v sub xo times 3.2 seconds. Oops, not meters, meters per second. Calculate maximum height and the time of travel before the ball hits the ground again. So we're assuming this ball is kicked from the ground. And here's where our components really come into play. I'm going to go ahead and draw what our motion looks like here. First of all, we leave the ground at a certain angle. The ball's going to fly through the air and it's going to land somewhere over there again. Okay? But I extend that initial velocity just a little bit so that we can see the specific angle it's leaving at. Okay. So let me draw this one more time. All right, first thing that we have to do, we have a velocity vector that's at an angle. Do we like working with things in angles? No, okay? So this velocity vector is v sub what? What's our resultant vector here for our velocity? V sub o. That's our initial velocity right there. And it's 20 meters per second? Okay, that's our initial velocity. Does v sub o fit in anywhere in our projectiles equations? Just plain v sub o? No, it doesn't. We have to break our initial velocity vector into its proper components. Okay, that's why we did so much work with components before projectiles. OMG. Okay. This side right here, what would I label this side? V sub y what? Perfect. V sub y o. And this side would be v sub xo. Okay? That's our initial velocity components. We can't solve this problem without breaking down that initial velocity vector. Okay? So let's go ahead and do that. V sub xo is equal to our hypotenuse times, this angle right here is 30 degrees, so v sub xo is sine or cosine? Cosine. So we're going to take 20 times cosine 37. I got 16, about 16, 15.97, but we'll round to 16. Okay, which means v sub yo will take our hypotenuse times sine of 37. Does this notation make sense to everyone? That's not a shortcut you're unfamiliar with, or does that make sense? Okay, great. So 20 sine 37 is 12 meters per second. We're solving for y, okay? And maximum height means we're really looking at our motion to about this point. Okay, we're only looking at half that process. So we're going to solve for y. What about our initial positions here? 0. X sub o is 0 because we choose that to be our origin point where our motion started out from. All right, so let's take a look at our equations. Can we solve using what we have here? Can we solve for y? I think we probably can. At peak height, what do we know about final velocity, final vertical velocity? 0. Okay, that's at peak height, which is what we're looking at right now. Right? So that means we could use our equation that says Vy squared equals V sub yo squared minus 2gy, or plus 2gy. Yeah? Okay, so if we know that our final vertical velocity at peak height is 0, our equation would look like this. 0 squared equals V sub yo, which is 12 squared, plus 2, negative 9.8, y. Okay, so that means I have negative 144 is equal to negative 19.6 times y. Be careful that in this term right here, you're not dividing by 2, because one equation is times 1/2, one equation is times 2. I see a lot of people mix that up and they'll divide by 2 there instead of multiplying by 2. So make sure we get that 19.6. Okay, that means our y, or our peak height, is what value? I got, 7.3 or 7.35 meters. Time. Couldn't we solve for our time to peak height and then multiply that by 2? Can we do it that way? Couldn't we also see that our initial height and our final height would be the same? They'd both be 0, right? Because it's landing in the same spot it started, or landing at the same height that it started. We can do it lots of different ways. Okay, so that's how I'm going to go about doing it. You can do it lots of different ways, but I'm going to solve time to peak height using this equation, V sub y equals V sub yo plus gt. So at peak height, my final vertical velocity is 0. And that means time for half the trip is 1.22. I'm going to multiply that by 2, and I'm going to get 2.44 seconds.